Okay, so welcome back from fall break. Hope you had some relaxing time off. As a reminder, we just had a midterm, so if you're looking for your scores, they should be available. I think Lockdown Browsers fixed it with new quizzes so that your stage one you should be able to view without having to go into Lockdown Browser. Stage two definitely can see. And then if you go into the midterm module, I released an annotated solution set. So it's all the answers, but then on ones that maybe take a little rationale, then I've sort of scribbled in like what the rationale is for those answers. So if you're looking for some explanation, then take a look at that. But then, of course, if you have any other questions, then let me know. Just send me a note or a Slack message, and I'm happy to help explain things. Otherwise, labs. So technically, last week was Lab 7, carries over to this week for flexibility. So that's due this upcoming weekend. And then next week, Lab 8. Now, Lab 8 will be a little bit different in that we're trying to model what you'll end up doing for your final project. So in Lab 8, I'm going to give you a bunch of data sets and then ask you to do input modeling on those data sets. And so there will be an assignment that is after Lab 8 that is your input modeling report that where you'll end up gathering a little bit of data, not all the data you need, but just showing you have access to your system and doing an input model for the real data that you'll use for your final project. And so Lab 8 is supposed to be a kind of practice for that, where I give you the data and then you end up doing some of the input modeling that we talk about in lecture and get to practice it then in lab. So that's those two. And then Lab 9 and 10 are on a regular schedule. And then the two last weeks are open labs that are for your final project modeling help. And so that's the idea that if you're working on your final project with your groups, you need some help building the models or understanding things, then those periods are available so that you have access to the TA who can help consult you on getting those things done. So that's the kind of schedule moving forward. And that hints at this final project. This is, in engineering, we stress group work and all that. So it is, I know to some people's dismay, a group project, but it's just one of those things that we all have to do, and you will have to do, in the future. I was up late last night finishing a grant proposal with a group of 11 people that I don't normally work with. So, it's a thing we've got to do. So these group projects, as hinted at the end of the exam and the little reminders, we went 4-person groups. So because of just the numbers, there will end up being 1, maybe 2, 3-person groups just to make things work out. But don't expect those, so try for 4. It's going to be one of those things where the 3-person groups will be ones that kind of at the end I have to kind of assemble, or it's kind of whoever's left over, that sort of thing. So plan for 4-person groups. How do you find your group members? Not everybody comes to class, not everybody goes to lab. So using Slack, using the discussion boards, and then if you go to the group project module, I have a Google Sheets link that is editable, and it's supposed to be a kind of clearinghouse for you to put in, do you need a group member to add to your group, or are you looking for a group to join? So you can add your name to that, and then periodically go back and check it to see that, you might have put your name in that I'm looking for a group to join, and then you come back and you find out that someone else is looking for a member to join their group. And you can't sort of always count on someone reaching out to you. And so if they haven't reached out to you but are looking for a person to join, then go back and contact them. And then to make it easier for everybody else, once you've made that match, it'd be great to remove your name from that sheet. And then once you have that match, then and I think I'll talk about this, but do it about a week and a half, is your names of your group members. And so I'm not looking for what project what system you're working on, anything like that. I'm just looking for everyone to submit what 4 people they're working with, not just one person for the group, everyone, so that I can confirm that everyone's in agreement. And then I'll form your Canvas groups based on that. And then basically everything else will be a group project where only one person will need to upload once I've created those Canvas groups. So that's how that works. So that's due it again, it's I think a week from Friday. So roughly a week and a half from now. So what is this project about? So the idea here is that we're trying to have you use Arena to analyze a real world system appropriately scoped for the amount of time that we have left and the fact that you guys are just starting at this. So it's not going to be super complex, but it has to be kind of complex enough that it makes sense that you need to build a simulation to answer the question that you're asking about. So common systems people choose in classes like this are coffee shops, restaurants, those banks, places where you can go, you can maybe sit there for a few hours, gather some data on arrivals, on services, those sorts of things, to start building input models of the types of demands and the supply of resources that those places have. And then you go in and you would, as an example, you might then build an as-is model. So a very simple model of the bank that for those arrivals produces, and those service times produces a similar amount of wait times. And then you might then say, well, what if we intervened? What if we introduced a kiosk system instead of live tellers? What if we, it can't be something as simple as, what if we add another teller? Does that reduce the time people have to wait? Well, we know, like there are I mean, just in general, how could it not? But if it's a more complex question that doesn't have an obvious answer, then you could say, well, there's one hypothesis would go this way, another hypothesis would go this way, and I'm going to use my simulation to test those hypotheses. And that's kind of the idea there. So complex enough to pose an interesting question, but not so complex that it's an unwieldy and very, very large model, especially because a lot of you might be using the student version of Arena if you're using it at home and not on the labs here in the Brickyard as well as on the remote. And so you'll be limited to 150 entities. And so if you get a very complex system, then you've got entities that are waiting all around and you can hit that 150 limit pretty quickly. So that's the idea here. I've given a couple of other ideas like small grocery stores, cafeterias, walk-only zones on campus, classrooms, laundromats. So things that you could get easy access to. People have also said, well, I'm doing an internship or maybe I'm doing a capstone project right now, and I actually have access to a bunch of data from a real factory floor. That's fine. Using that data would also be fine. If this overlaps with your capstone, we want to make sure that it's okay to work on the same project as your capstone, but you might have slightly different team members there than here. And so I want to make sure the deliverables are distinct. So you might use, be motivated by similar problems, be using the same data. You might be using a simulation in capstone. That's perfectly fine. That'd be great. But there's a limit to how much you can double dip. So some of that you can certainly use, that kind of supply chain of data and problems. But then at some point you need to kind of fork off and say, okay, but maybe this subset of the problem, this small problem, I'm going to kind of cut off a little bit of that, and that will be what I'll use for 475. And then this bigger problem that's of interest to the stakeholders in my capstone, I'll use that for capstone. That's perfectly reasonable. We've had people also they say, oh, if my dad runs a guitar manufacturer, he's a guitar manufacturer, he's a luthier, and we have a bunch of stuff on orders and things. Can I use that? And that is perfectly fine too. You don't have to go out with a stopwatch measuring arrival rates and so on. And they're also interesting. So back during COVID, when we taught the class, we couldn't bring students together to gather data. It was just generally hard to figure out where to get data. And so we've learned that some students can actually use webcams that are watching intersections all over the world, and then they can model those, like how busy is this intersection at different times of day, and those sorts of things. So there are other ways you can gather data. So a lot of different options to think about, but the first thing to think about is who's on your team. And that's that, 4 names due about a week and a half from now. And so it's due on a Friday, and that gives me the weekend to wrangle people if I notice that there's certain people that aren't allocated to groups or whatever. Then I can bug them and bug others and try to force groups together. But I prefer not to do that. So please try to pick your own 3 partners for your 4-person group. Okay. I think that's probably, oh yeah. So then I've got the deliver. So let me go back. So yeah, these are the deliverables that I was talking about. Names of teams members due next week on Friday. And then once you form that, then I think it's like maybe a 2 weeks or so after that, then you do that input modeling report. So we'll talk more about that as we get closer to it, but that's, you're gonna have to sort of prove in a very short report, then you're gonna like, it's like, 2 pages or something like that. Then you are going to have to show that you have access to the system, you can gather some data from the system, and you can practice input modeling on the system and sort of justify what are the key problems of the system, what, excuse me, types of data might you end up gathering as you move forward to the project. And that will give me an opportunity to give you feedback on these things, whether it's too ambitious, not ambitious enough, and so on. And then we basically leave you alone. So then the next deliverable is during the last week of class before finals week, then you'll upload a final report, which will be 4 pages with a very specific format that I have online, and a up to, but preferably shorter than 10-minute presentation where not everyone has to present. It's not one of those sorts of things because different people can participate in different ways. We don't present in class. We upload to Canvas, and you do that on the Wednesday, the middle of that week, so that I can then assign peer reviews assignments. So then by the Saturday of that week, so you've got Thursday, Friday, and then if you need it, Saturday, then you have to watch a presentation and read a report and fill out a rubric on one of your peers. And those peer reviews, those will be individual assignments, but everything else will be group assignments. So that's how that will work. And then I do use some of the peer reviews as to modulate the grades that I give on the oral presentations and the final reports. And so how well you convinced your peers does end up playing a role in your grade. Okay, so I just mentioned that 10-minute presentations, very specific format for the 4-page report. And I think and then start soon, form your team. So I think that's pretty much it on the final project. So before I get back to homeworks and things like that, any questions about the final project? What's expected? Okay. All right, so then otherwise, the other things looking forward, assignments due from now until the end of the semester, there's only 2 more homeworks. So there's homework G3, which is out. It's one that you're going to revisit the chi-squared test, but for a general distribution. So this is something that I think either in 380 or 385, you've done this before. So we're sort of reminding us of that. And then we're also going to talk about something called a power analysis, which I don't think you've done in 380 and 385, but is important for figuring out how many replications you need to run for your simulations. And then there's the last homework H. This is one that will be much more like a lab. This is, I'm sorry, the J2 will be much more like a lab. So there's, yeah, I'm sorry. So homework H is the one I was talking about that has got the chi-squared test and so on. And then J2, that's the one that is the second. So you only have 2 homeworks, H and J2. J2 is the one that will be much more like a lab. You can't drop that one because we use that for ABET metrics. And so you're also not going to get a solution set for it. So it helps us measure progress from semester to semester. And so that one, again, is going to be a little bit more like a merger of lecture and lab. You're going to do some arena in it. You're going to solve some problems, make some modifications to the model, do some analysis. So it's a little bit of a synthesis homework. And so those are the homeworks there. And then you've got these ICAs. So those are very similar to before the midterm. And then, of course, just keep thinking about your final projects. So that's the schedule moving forward. Any questions? Okay, great. Hopefully the midterm wasn't too horrible. I thought the distributions were good, were as expected, were maybe even the averages were slightly higher than I expected, which isn't a bad thing at all. So I thought so great job for everybody that did that. And I also saw a lot of nice improvement from stage 1 to stage 2. I was here for stage 2, so I listened to a subset of the groups talk through problems, and there are a lot of very productive conversations there. So nice work working together for that. Okay, so where were we last time? Eons ago before the midterms. So we were talking about random variate generation. So we were talking about this inverse transform method where we can get these things out of a computer easy, but what we really need are these things down here, which requires us to build these cumulative distribution functions and invert them. And so that's this method. So you will periodically get a probability density function like this one, and then you have to go through this. Now, as some of you may have started to realize, you can kind of think through these things geometrically, and it often goes faster that way rather than trying to go through the formal process of inverting. So, if you look at this thing here, it's just a triangle. So up to this point in X, it's the area of this triangle, and 1/2 base times height. So you can say, well, up to this point, it's just 1/2 base times height. That's this thing here. And then at some particular point, and then you could invert that. So that's what we're saying here. So once you have the 1/2 base times height, then for this region, this is how you invert it. But then eventually you get to this point here. And then at this point here, rather than worrying about all the integration by all the pieces and adding them all together, then you realize that, well, the area underneath this curve is just this entire triangle plus this rectangle. Well, this entire triangle, 1/2 base times height, is just 1/2. And then this rectangle, well, it's whatever my X value is minus 1, that's this leg or this width. And then the height is just 1. So then I just get this X minus 1 is my little rectangle here. So if I got this 1/2 plus X minus 1, that's my area underneath the curve. And bam, you got your CDF. And so tricks like this can make these things go a lot faster in practice. I think that for the midterm, all I really gave you was a uniform for you to have to worry about, inverting. And I heard people like in stage 2, you remember the formula for generating uniform random numbers. But even if you didn't, if you just remembered that it's kind of flat, then you can kind of do this process in your head. So, you go through this process, you generate those things, and you get one of these, and then you have to implement it. And so, we've talked about, and you've now had practice at doing that. So this is just a review on how to do that. And you get a histogram that looks like this, and this looks roughly like what we were expecting. So that's good. That's at least has some face validity. It looks right. So that's great. And if I want to do it in MATLAB, here's the MATLAB version of it. So that's a way of generating a bunch of random numbers and then partitioning those random numbers. And so that certain ones have one formula applied to them, the other ones have another formula applied together, put together a histogram, same idea, also get that. And then you can even then do it in Arena. It's a little uglier in Arena because remember, Arena is a simulation program. It's not really a data visualization program. The data that comes out of it is just meant to be quick and dirty for you as the engineer to just do a quick, validation. So in Arena, you can implement this using an assign block. I kind of show that how to do here. I'm not going to quiz you on this, but just showing you it is possible to do that. And then as you were, I think, playing with now in Lab 7, there are visualizations. So there's a histogram visualization you can drop right on your Arena diagram. And you can say, I've been generating a bunch of numbers at this point in the block diagram. What do they look like? And it can give you a quick histogram. It's not as nice looking as the other two, but it's pretty much the one that I wanted there. So going from the PDF to the validation step, we're getting that. That's great. And so, you could do this for another example. So I just put this here so that if you want, you can flip through it. I'm not going to go through that in detail, but the same sort of idea, you get the histograms and so on. But so at this point, if I generate these, so before I said, if you gave you this and asked you to generate that, we know how to do that. And we can see that this looks roughly like what we were expecting. But normally we're doing the opposite. So input modeling is really like you're going to go out and collect data. So you're going to start with this. And then you're going to say, all right, what PDF goes with that? and how do I know that this is the best one for that? That's really now what we're pivoting to. And then, and then the big question is, once I've generated this PDF, then I have to ask myself, have I done a good job? How do I know that this particular PDF is a good match, the best match I can get to these data right here? Whereas, not some other PDF that might have a slight nuance difference. And so that's kind of what we're dealing with now. We've seen this for the uniform. So, we've seen like, okay, we generate random numbers that look roughly uniform. This is what they're trying to look like. This is what the PDF should look like. And we already know that things like the chi-squared test, the KS test, can help us speak to, are these uniform enough? But now we need to modify those tools to allow us to do that for more general distributions. And that's what we're going to sort of start talking about in this unit. So yeah, basically doing that for these general distributions. That's where we're moving forward. So let's further motivate that and then get into the first kind of components of this unit. So this is our motivational model, very simple arena model. These are the older block diagrams, so they don't have the same colors. You notice in the new version of arena, the blocks are colored with the panel that they're from. So that's kind of nice in that if you're looking for a block and you're trying to figure out where it is, you can say, well, I've already got one of those in here and it's red. Well, I need to go to the red panel to find it. So that was one of the innovations that they came up with at Rockwell in their refresh of the interface. So these are the old ones. They're all yellow. They're all Simpsons colored. And so you've got these inputs, this arrival process. You've got this process here of checking for IDs. And then you've got a certain set of passengers are cleared and a certain set of passengers are denied. All of these things are things that we need to fit from data, but we're going to focus on just the arrival process right now. So in this arrival process, you look at your data and you get variation. And so as we know, we're going to then try to fit a probability distribution to the variation we see from reality that people arrive at with different spacing. So we get data that maybe look like this. And if you measure arrival data, you will find that it often looks very kind of exponential for reasons that we kind of defined, like all of the assumptions of an exponential. If you think about them, a lot of arrival processes have approximately those assumptions. And so you don't see bell curves for arrival processes. You generally see these sort of asymmetric things. And sometimes they're not quite exponential, but they're usually shaped roughly like this. Unless you've got some filter that prevents things from occurring like clustered right on top of each other, they usually have this kind of ski slope shape. So you get data like these, and we could say, well, we're going to assume that it's exponential. We have to be able to evaluate whether that was a good choice. But let's say we've decided it's the right family. So then the next step is then saying, well, which exponential? And so I see the mean outcome as 19.88. So I need a way to say, well, if the average is 19.88 in my samples, what's the best mean that I should put into arena? And so, and we need to be able to justify that choice. So for now, let's just say that we use the mean without justification, the actual mean, we're just going to dump into arena. We go into this block, we say we're going to have an exponential. We're going to use the mean from our real data, make sure our units are correct, because that's, it may default to minutes. Like your simulation units might be in minutes, so then maybe this will default to minutes, but your arrivals happen at levels of seconds. So be very careful about that. That's a common mistake at first. People are noticing like, I've got an extremely idle system, and it's usually because, well, your arrival process is working at a different time unit. So, you put this stuff in, an exponential with this mean that matches my data, and you run that through your simulation, and you get outputs here. So this is back when Arena used crystal reports, it looked like this, but now you can find these in the Excel spreadsheet. And so you can find the average waiting time and half width. So you know that the waiting times, every customer has a different waiting time. And so you get variation there. And so you want to ask, what's the average waiting time for the population of customers? And because you're only running a finite number of replications, that is going to have noise. And so this half width tells you whether, where the true average is likely to be. It's likely to be 6.4 plus or minus 1.2. It's like, we're getting, we're starting, it's a very political season. We've got a local election coming up. And, people talk about, within the margin of error. Well, what they're talking about are confidence intervals, 95% confidence intervals. And what they mean is if you could say, well, there's 49% plus or minus 2%, then what that means is that the real population could be anywhere from 47% to 51% in favor. So that would mean it's within the margin of error. That means we don't know what the real one is, but our estimate from our limited polls is that it's probably in this range. So if that whole range is above 50% or below 50%, then you know that then you can conclude that the population is probably, it's in favor of one position or the other. But if it includes 50%, you can't say anything. That's what they mean. It's within the margin of error. And that's just a confidence interval. So likewise here, if your boss says, we want to make sure we have less than or we want to make sure we have less than a 10-minute waiting time, then you can say, well, 6.4 plus 1.2, that's still way less than 10. So I don't know what the real waiting time is, but this waiting time, definitely 10, it's very, very unlikely that it's actually 10. But if your boss says, we want to make sure the waiting time is less than 7, well, 7 is within this. And so the waiting time might be less than 7 or might not be. So we get variation out is what I'm trying to say here. And that variation came from our variation in. If you just had a constant arrival rate, then you would have you wouldn't have the variation here. This would just be this half width would be like 0. It would just be every replication would be exactly the same. But some replications, you have one set of customers, and other replications, other set. So there's variation within and across replications. And that's what generates this variation here. This variation here is what you show to your boss. But that variation comes from this variation, from the input models. And that's why we have this garbage in, garbage out we have to worry about. So half of this class is building those Simpson-colored or green and red colored block diagrams. And if you can do that, that's great. You can build a sim. But the other half of this class is building input models that couple with their diagrams, because the variation you get on the output comes from the variation you get on the input. So if you choose the wrong variation on the input, you'll get nonsensical variation on the output. And so that's why we have to focus so much on input modeling before we start building our sims. Got to choose the right input variation before we can start using it in sims of real systems. That's the motivation behind all of this. So input modeling, we emphasize this before the midterm. It selects probabilistic models that mimic realistic variation. Fortunately, for certain types of systems, you know what inputs you're definitely going to need. So queuing models, like you might see in 470 a lot, you know that every node of a queuing model, you're going to have to worry about inter-arrival times and service times. That's what it means to be a queuing model. You don't know how often things are going to arrive, and you don't know how quickly they're going to leave that node. Alternatively, if somebody comes to you and says, we have a supply chain problem, your first question to that stakeholder is, what do you know about your demand distribution? Because that's the big thing with supply chain is, how many objects do you keep on hand to sell to customers? Well, that is going to depend on what your customers are going to want on average or the variation in that. And then the other thing that's going to matter is lead time. So if you're running low and you know you got customers coming the next day, how long is it going to take to restock? So if somebody says, I want you to build me a supply chain simulation, your immediate question is, what information do you have on your demand distributions and your lead times? And then likewise, if you're doing a reliability problem. So people are saying that, I want to model how often or what are the costs or how often does my factory break down? And then you have to say, well, okay, so what are the resources in your factory? And do you know the distributions of how often they fail. And if they say no, then before you even build your model, you have to go into that factory and gather data to try to estimate these failure times. So if you know what type of problem you're working on, you immediately know at least what inputs you're going to need. But some problems don't quite fit these models, and then you have to then figure out what inputs you need. And so you're going to go out there and you're going to say, well, I thought these are the inputs I need, but once I started building my model, I realized that actually there's another input here, that I confounded two things. I need to break some things apart. And we're going to see examples of that, where so choosing your inputs is not always trivial. If you're lucky enough to get a nice package problem like this, these are the inputs. But a lot of problems, you have to then discover what all the right inputs are and discover, are there data on these inputs? So that's the kind of motivation there. And so with that motivation in mind, then in this unit, this 3-lecture unit, we're going to talk about how do you collect data from the system. Once you have that data, how do you identify the right family or the probability distribution to represent the shape of that data? And then how do you choose once you're in the right family, how do you choose the right family member? Exactly which of that, which exponential, which Gaussian, et cetera. And then once you have the precise distribution that is your candidate, evaluate that distribution. So how well did I do? Does this actually look like the data I was given or I collected? So that's our kind of roadmap. And then for the rest of today, I just want to talk about data collection. So that's where we're going here. All right, any questions about any of that? Those anecdotes or ramblings? Pretty clear. Hopefully it's becoming clearer as you're starting to work on these basic models in the labs, where these input models fit, and so on. Okay. And people really do use this stuff. I've had students from my class that go to work at Disney. They come back and they give presentations to Sky, and they build simulation models of the theme park, and trying to, better operate rides and things like that. And so, Disney is primarily a queuing model, but there are aspects of it that are also a supply chain model. Like, do I have enough inventory of certain things that I need to run this ride or to supply this demand and so on? So, you can couple these things together. Even something like a amusement park is a complex system that you really don't have math for, so you end up building sims for. Okay, so another example here. Let's assume that we're talking about a simulation study, not about Disney, but about a clinic, about a medical clinic that has patients, and the key resource that we're focusing on is a nurse whose activity is obtaining patient history. So we're trying to model that. Maybe we're trying to optimize that to better, to streamline this process to try to get patients in to see the doctor sooner. So a prior study from, more than 20 years ago is collected timing data on nurses taking patient histories. Those data are available. They're right there. They've been digitized. They're on the machine. You can feel free to use them. And you can put them right into your model. So the question is, should you use these data? Why or why not? What do you think? Are these data you should pay any attention to? I mean, I'll tell you an example. So Doug Montgomery, sort of a famous statistician who was here in the department, kind of phasing into retirement. He used to work for a bunch of these big industrial companies. And he would talk about, to go into it, and he would propose, like, we really need to do an experiment to figure out these properties of these carpet tiles, if it was a carpet tile manufacturing company and so on. And he would frequently get the people coming back and saying, no, we don't need to pay you money to do that study. We already did that study years ago or even recently, and here are the data for that. And so sometimes those data were useful, but other times Doug would talk about how, that he was, it was really important for him to understand the role of temperature in these carpet tiles, in this particular case there. And so he wanted to run an experiment where you saw how long it took for these carpet tiles to fail or to adhere under different temperature regimes. And they said, no, we already have data on the carpet tiles, and here you go. And when he came out of it, he was surprised to find the temperature had like no effect. And when he came back to them and gave his presentation on the stats that he ran or whatever, and he said, and I expected to see a response to temperature, and but there really wasn't one, so we ended up not including temperature in our model. And then they said, oh, yeah, well, the data we gave you, we actually controlled temperature tightly, so there was no variation in temperature. So the reason you didn't see any effect is that every single carpet tile had the exact same temperature. And so they said, well, that's why I wanted to run my own study where I could have varied that. So that's what I mean, just because the data are available, there can be flaws in the assumptions that you can use that data. So what might be the flaws in these data here? So from your own personal experience, going to have your own patient history taken, what might be a problem with using data on the time it takes a nurse to obtain patient history from 20 years ago? Yeah, I mean, so that's nowadays, if somebody takes your history, they probably have there might be a machine bolted to a wall that they bring over, or they've got a tablet or a laptop, whatever. I mean, they might take your history in the lobby, with a mobile unit or something like that. They might have you give a lot of your history ahead of time before you even arrive there because it's online. 20 years ago, you go into a clinic's office and there's paperwork you have to fill out. Then you go into a room and then the nurse is filling out paperwork themselves. So it's a completely different process, and it's just slower to enter those data. And so if you end up using their data, you're optimizing the operation from 20 years ago. You're not optimizing this operation. So in that case, you'd have to say, I appreciate you have the data, but here are the reasons why we really need to invest in more data collection, even though it's going to be costly, because I just can't use those data. So you have to sort of think those things through, because it's costly to collect data. And then other things you have to look out for. Summary statistics are not the whole story. So we've got a simulation study assessing the impact of new security protocols in a metal detector going into a government building. Our entities are people. Activities include the time to pass through the metal detector, where the metal detector is the resource. So they say, I want you to optimize our security protocols so that we can get people into the building quicker, reduce these lines. So they take 1,000 observations at some point, and the mean and standard deviation are nearly identical. And so, and that's all you know right now. The mean and standard deviation are nearly identical. Are there probability distributions that you know of where the mean and standard deviation are nearly identical? Anybody remember that? It was on our sort of, our cheat sheet of probability distributions. There was a continuous distribution where the mean and standard deviation were identical. A one-parameter distribution, one of our few one-parameter distributions. It's like our favorite distribution. Our favorite one-parameter distribution. What's a one-parameter distribution for time that, yeah, that's it. What's a one-parameter distribution for time? So it's non-negative. Exponential. So you think about that, you say, aha, what's a probability distribution is the mean and standard deviation are nearly identical that is non-negative? That's an exponential. It sounds like an exponential. An exponential's mean and standard deviation are nearly identical. So I think, okay, this has got to be an exponential without even looking at the data. But then they say the mean passage time is 30 seconds. And then you have to think, you either have to ask a domain expert, or sometimes you have to trust your own gut if you're familiar with these systems and say, does this make sense? So this is saying the time it takes to walk through a metal detector, just that much, not getting checked for screening or anything like that, just to walk through a metal detector on average is 30 seconds. That would mean that sometimes it's longer, sometimes it's shorter. Does that, does that pass your gut check? Does it seem like that makes sense? I mean, a metal detector is, it's like me, that's it. That's a metal detector. You could, maybe there might be somebody who's geriatric, who's injured. and maybe it takes them a little bit longer. They have, they walk a little bit more slow. But if I were to count down 30 seconds to go over this step, it would be excruciating for everyone in this room, more than my current lecture. And so that is probably an indication that there's probably an exponential with a mean of 30 seconds is probably the wrong distribution, because that's going to give you people that take way too long. It's like a dog trying to investigate the ocean the first time they've ever met it. It'd be like, oh, do I go in? Do I go out? It just walk through the metal detector. So that's probably not the right thing. So that's why you always want to look at distributions. You always want to plot it. You always want to look at the shape of the distribution. So you take a histogram of the data that they have available. And what you find is that despite its mean passage time being 30 seconds, it's a bimodal distribution, meaning that it's got a big hump close to 0, and it's got like a big hump close to 60 seconds or so. And so those two big humps do not look like an exponential at all. And it just happened to be that things balanced out, that the standard deviation and the mean were roughly close to each other. So we were expecting exponential because we're just primed to think that way with time. We saw the mean and standard deviation were the same. So our gut took us to exponential, but then our gut check here, said, at 30 seconds, that seems a little long. Let's do the histogram. So always do the histogram. You can see it's not exponential. And it actually, this is one of those cases where it suggests we need 2 input models. We're probably going to need an input model for the population that goes through the metal detector fast, and a population for the model or a model for the population that goes through slow. And then we have to figure out why they're going through slow. And it turns out that maybe the reason they're going through slow is they're getting flagged for extra screening, which means now we need input models for all of the extra screening processes. So this is an example where looking at the histogram helps inform which input models to pick and how many of them. And we'll do a more detailed version of this in the next lecture. So we'll kind of walk through the steps of that. All right, and then data values not being what you expect. So we see that sometimes passage times in this same system are negatives. So this is going to happen. There's just things that duration should never be negative, but the way things are calculated, sometimes you get rounding errors that go the wrong way, and you end up getting these negatives, or somebody might have recorded the wrong time. So we have to figure out, are these garbage data? If it's a fixable mistake, like if it's a rounding error, then I can say, well, any small negative number, I'm just going to assume is 0, and maybe that'll be fine. I'm just going to fix it to 0. But if it's a really big negative number, then that might indicate that I just have to throw that data point out. But does that data point have other information in it? Like, not only that row of data might tell them how long that took them to go through the metal detector, but it might also indicate whether the metal detector went off. So if I throw out that data, then am I also throwing out the data about the probability of triggering the metal detector? So how safe can I just say, well, throw out the time, but keep the detection? Can I do those sorts of things? Can I ask the stakeholder, what if the stakeholder doesn't know? What are the consequences for those things? Or things you have to think through from here. So that's what kind of we're talking about here. So when you get a data set, you often need to clean that data set. So when you get a data set, sort it, see what is the range of values? Does this range make sense? Plot the histogram. Does this histogram make sense? What does that tell me about it? Those sorts of things. I need to do all of those things before I can be comfortable with turning these data into a distribution. Because when you do an automated fitting process, the computer doesn't know that you don't want negative numbers, and it's going to fit. And if it fits something that can generate negative numbers, you're going to run your sim, and you're going to have customers or passengers or whatever who are going back in time, where as they go through the metal detector, suddenly they're at a previous time in the sim. And that doesn't make any sense. You probably don't want that. So you have to be very, very careful when you use data to generate models, because then those models are just unleashed into the wild of your sim, and you trust that they're going to work right. So you really have to be careful about the data that you were used to generate those models. Okay, so any questions about that? All right, so how do we do this responsibly? So pre-observation and planning. Oh, didn't mean to do that. So what we mean by that is, if you decide for your final project to, you're going to do the Chase Bank on, Broadway Road or something like that, maybe go and check it out ahead of time. Just take a look and say, all right, I think a bank should operate this way, but you might find that that particular bank has got its own little nuances. And so go, and before you even study, just go out there and take a look, do some pre-observation, maybe gather a little pilot data, do some planning. Like, what are all of the things that I want to model about this thing? Then analyze data while it's being collected. You have to be careful about this because you don't want to bias your results. So you don't want to, say, oh, now that I've seen certain phenomenon, I'm going to change the way I'm collecting my data to capture more of those. That's not it. But you don't want to look for errors. Like, you start noticing that you're collecting a bunch of data that are turning into negative numbers, then you can say, well, there's something wrong there. Or as you're analyzing the data, if you're noticing that that you're getting these bimodal distributions and data that you really were expecting a unimodal distribution, then that might tell you actually need to be collecting more data. So it might be that you go to Subway and you're trying to collect the whole data it takes to make the sandwich, but it turns out that that's not kind of turning into the nice unimodal distribution you want. So you really do need to say, well, how much time does it take to cut the bread, to add the meat, to add the cheese, and so on? So maybe you do need to break those things up because there's something special about this system that creates correlations. Maybe it's the same person who cuts the bread as, does the cheese. And so those two things become highly correlated with each other. And so those two might need to be, maybe you need to handle those differently. So, that's, you have to do that kind of, by doing that analysis, it tells you, do you need to go back and make some revisions? And then there's this check for homogeneity, which we've talked about a couple of times, pooling. So this idea that you're going to collect data at different hours of the day and different days of the week, conceivably. And so if multiple days of the week behave the same, or multiple hours of the day behave the same, you can add all of those data points together and you'll get a better model because you got more data points going into that model. But you can only do that if you're confident that the distribution of those hours are very similar to each other. So, it might be that the arrival rate for 10 a.m. and 9 a.m. look very similar, but 11 a.m. It starts looking differently. So there are statistical tools that allow you to compare. Is it likely that you can do a chi-squared test on two distributions? So far, we've done a chi-squared test on an expected distribution and an observed distribution. You can do a chi-squared test on two observed distributions and say, does this observed distribution, is it likely coming from the same distribution as this observed distribution, chi-squared? And then if the chi-squared finds very little difference between them, then you might say, I'm going to assume that these are the same distributions and pool those data so that I can get a higher confidence estimate of the distribution for both of those hours of the day. But if your chi-squared test rejects that and says 9 a.m. is totally different than 10 a.m., you're stuck. You just have to have a 9 a.m. model and a 10 a.m. model. And in your sim, you have to schedule that it switches from one model to the other. So checking for homogeneity makes for better models, but also not assuming homogeneity. Like, you just can't say, well, all right, so I'm going to go to the Subway Monday at 9 a.m. and gather a little bit of data. I'll have my teammate go to the Subway Thursday at 4 p.m. and gather a little data. And we're just going to put all that data in a pool together, and that's how we're going to estimate arrival rate. Well, the 9 a.m. arrival rate is probably very different than the 4 p.m. arrival rate another day. And so you probably can't pool those things together. Now, maybe you do the test and you say, oh, look, they're actually very similar. Then you pool it together. But if they're very different, then you got to say, well, maybe we're going to have to simulate morning and afternoons. And 9 a.m. will be our model morning, and 4 p.m. will be our model afternoon. And we're just going to have the sim switch between the two of them because we can't justify putting them together. So questions about that. Is that clear what I mean by homogeneity? Looking for assuming homogeneity, looking for heterogeneity or inhomogeneity. You've already started working with schedules in Arena, I think, by this point, and this is where you use schedules. Okay. Data censoring. So this is a big one that, if you're looking for how often does a certain event happen, and you never watch the system long enough to allow the event to happen, you will then assume that the event never happens. So that's what we mean by data censoring, effects of stopping watching the system. So I recently had a bunch of postdocs who worked for me. They ran a simulation and they put together a report, and we were presenting it to our government stakeholders. And I was noticing in the histograms they put together, a bunch of things were clumping at what was a simulation time, which was supposed to be like a performance criteria, if the particular system we were simulating took longer than this amount of time in the simulated world, it was a failure. And it's like, so for certain really difficult cases, we just had a cluster right at that failure time. And so I asked the postdocs, and they said, well, we just stop the sim whenever we hit the failure time. And it made a little bit of sense, but the downside of that is now we lost information about what was causing that particular robot, for example, in that sim to take longer. Because we censored them, we cut them all off at the same point. So if we let them go, we might have seen that under this condition, this robot took twice as long as what was allowed, but under this condition, it took half as long, and so on. We could have seen that distribution, but we got rid of all of that, and across now all of our conditions, it looked like they took exactly 60 minutes. And so we would then infer that 60 minutes is a magical time that all robots break. But in reality, if we would have let them go, there would have been variation there that would have been very useful and informative. So, stopping your data collection early can lead to problems in your inferences. And so, failure time distributions, that's the easier case there. We've never seen one of these light bulbs fail while we're in this class. So if we were to estimate the failure time distribution of these light bulbs, it would be infinite. They just last all the time. But we know that's not actually the case. So how do we deal with that? And it's outside the scope of this class, but for those that are interested in it, there are tools like so-called survival analysis. This is a statistical tool that allows you to correct for this. And so if you're running a medical trial, you're seeing like how long until we get adverse effects. Well, if the medical trial only runs a year, but an adverse effect doesn't happen, for some until a year and a half, how do you deal with that? And there are things like survival analysis that help you detect whether the survival curve really is consistent with absolutely no adverse effects. So as if you start getting a few adverse effects before you censor, then it sort of doesn't make it that the other ones that hadn't had those effects, it doesn't sort of predict ahead of time that, oh, well, they're definitely never going to fail. It provides sort of a probability that you will get failures in the future. So you have to be careful about, you can't collect data forever. So you're going to stop somewhere, but when you stop, that's going to have a consequence on your inferences. So you have to be very careful about when you choose to stop and how. And then the other sort of complex thing is looking for relationships between variables. So these are just synthetic data that I put together, but these are inter-arrival times and service times. So this type of plot, I put a scatter plot here where every inter-arrival time is paired with a service time. So imagine if it's at Subway sub shop, customer walks in, how much time did we wait before that customer came in? That's their inter-arrival time. And then how long did it take for them to get their sub? Once they ordered it, that's their service time. I can plot them together in one point as this scatter plot. And then I can marginalize each one of these variables. So that means I can take a histogram of the inter-arrival times separately and a histogram of the service times separately. So I get the so-called marginal distribution of this joint distribution. And those are these two marginals. So that's why I've got a histogram on the side and a histogram on the side. So notice here, in both of these plots, the histograms on the X and Y axis are the same. So this is the exact same service time distribution and the exact same inter-arrival time distribution. But I sorted the relationship between interarrival times and service times differently here versus here. So over here, I have no relationship, there's no correlation between interarrival time and service time. But here, I've got a correlation where those that had, for some reason, those that had a big gap before they arrived also had a longer service. And those that had a short gap had a shorter service. This might be because in a rush, the system sort of ramps up, like people start making the subs faster. So when people arrive more quickly, it changes the service time distribution. But if people have gaps, then they're maybe slower, and maybe that's what creates this correlation. Who knows what causes it? But the point I'm trying to make here is if you only looked at these two histograms, if you only gathered service time and gathered interarrival time, there's no difference between these two cases. But if you plot them together and you notice that you get this cigar shape here, then you realize that, oh, these aren't two independent processes. I need to make sure that when someone comes in, I use their interarrival time to generate their service time, or else I won't capture this correlation. Is that clear, these two plots? I might show plots like these on a final exam with these marginal distributions and so on. So I want to make sure that you can interpret these plots. So what do you do when you see these sorts of correlations? Now, there are complex ways to do that. So in some of the extra slides at the end of lecture E2, I talk about NORTA, which is a method for regenerating these types of things. It's a little more advanced method, so I won't quiz you about that. But if you're interested, check out the slides at the back of lecture E2. But a simpler example is you can basically do a regression. You can fit a line through this cigar, and you can say that, roughly speaking, that line is going to look like it has a 2.5 slope. So if I know the interarrival time, I multiply it by 2.5, but then it's got residual variance. And so then I'm going to add a normal distribution that gives me some negative or some positive, and then that would potentially give me something that models this pretty well. So that's a way that I can build correlations. And then notice here then that now, once I have my interarrival time, the input model is this residual variance. So how much variance in service time is not explained by interarrival time? That becomes my input modeling problem. How do I model this into one here? So that's something that I can do. And how do I implement that? So there's the kind of recipe for how you could go through and implement this thing here inside ARENA, so that you take an interarrival time that was drawn by ARENA, and then you end up generating a service time based on it. So there are ways to do that in ARENA. So questions about this general idea of when you see a correlation, building these dependent models where one duration, one activity is correlated to another activity. Does that make sense? Yeah.
Just what you said about residual variance.
Yeah. So if I were to plot, if I get rid of this, so this what this is saying here is that service times is 2.5 times interarrival time plus a random draw from a normal distribution with a mean of 2 and a variance of 1. That's how this is interpreted here. If I didn't have this random draw here, then there'd be a deterministic relationship between interarrival time and service time. So if you knew the interarrival time, you would know exactly the service time. And so this plot here would just be a straight line with a 2.5 slope. But we know that interarrival time doesn't predict service time perfectly. And so I have to add a little bit of noise. And that's what this here is. This is saying that I'm adding a Gaussian that has a mean of 2 with a variance of 1 to this deterministic relationship. And so then the question is, so basically, if you subtracted this line, this 2.5 times arrival time, you could subtract that line, and then you would get a cloud of points that wouldn't be sloped. They would just be like a horizontal cigar. And then you could say that horizontal cigar, that is the statistics of that horizontal cigar. If I collapse them together and take that histogram, that is this distribution. So now my input modeling problem is not modeling service times, But modeling, this is what we refer to as the residual error, the residual variance. So once you've addressed inter-arrival times component on service time, what's left over? And this is the error. So modeling the error becomes your input model. Questions on that? Does that help? Great. All right. And then also autocorrelation, something that we've introduced a little bit. Now we're going to see a little bit more. Up here, these are example of independent samples. And so you can imagine this is service time, and this is 1,000 customers. And so maybe this isn't service time because it goes negative. Maybe this is that residual error I was talking about since it's negative. But the point is, the thing on the y-axis is something you can measure. The thing on the x-axis are instances where you can measure it, like customers. So you've got 1,000 customers, you take a bunch of these samples, and these are independent. And what that means here is that one customer doesn't tell you anything about the next customer. There's no pattern from sample to sample to sample. So if I were to plot down here a sample value on the x-axis and then a scatter plot with the sample value that is 10 points later. So basically, I take a point here, like this point that's down here, and then I go 10 samples to the future, and I find this point here, and then I pair those things together, and that's how I generate a single point of this plot. If I were to do that for every one of these things, then I generate this plot here with, and we refer to the time between them as a lag. So this is a correlation plot and autocorrelation plot at lag 10, where I'm studying then the correlation between a data point and another data point 10 samples later. And this shows me, because it has no shape, it goes everywhere, there's no correlation. And that's what we mean by it's independent. And so if I did this for lag 10, that's great, but it could be there's a correlation at lag 8, at lag 2, at lag 1. So I need to do it for all of the lags, and that's where I get this so-called correlelogram. And so I've got all of my lags here, and I've got my correlation coefficients on the y-axis. So this would have a 0 correlation coefficient, and this is suggesting that every other lag would have a 0 correlation coefficient. So this is a correlelogram, and when your correlelogram is flat, then we refer to that as white noise. So there's no correlation in the noise that we receive from the sun. That's why the sun looks white. So that's where we get this term white noise. Now, if instead I got this signal, then this is a noisy signal, but it looks like generally there's a trend where we get this upward value followed by downward. So here it does look like for short lags, you can predict roughly where the distribution is going to be. So if I'm up here at 0.2, for short lags, I can assume I'm going to be close to 0.2. For long lags, I don't know where I'm going to be, but for short lags, I'll be near 0.2. So this does have autocorrelation. So if I were to plot a lag 10 scatter plot here, I do get a cigar shape. So it suggests that knowing one point predicts the point 10 samples later. If I were to do that for every lag, I get this thing that has a lot more structure. It is not just a flat line. And so it has color. So if you've ever heard of pink noise, green noise, brown noise to some extent, like if you have white noise generators, some people now, instead of listening to white noise to go to sleep, they listen to green noise or listen to pink noise. That pink, for example, that comes from autocorrelation. That is actually saying that the noise that you hear is correlated with it, so that you have more low frequencies than high frequencies. So if you were to plot it out, the sound pressure levels, it would look more like this than it would look like the previous plot. And so when you see structure like this, then that shows us that we don't have independence. And so this tells us here that there is strong correlation up to lag 1 or whatever. Then for intermediate certain lags, it goes to like no correlation. But then there are these beats where at certain lags, you get correlation back again. And that's resonance. So that's this idea that like you can kind of see that there's sort of a sine wave or a cosine that's going on here. And so when you hit different, resonant peaks, different multiples of that, then you find that you can have zero correlation between, but then high correlation at those peaks, at those periods, or at those multiples of periods. And that's kind of what we're seeing here in this plot. So you have to look for autocorrelation, and tools like ARENA have ways to do these correlograms for you so you can look for that. And if you have that, then there are ways you can build it into your model. So here is just one example of an expression where you could say, I'm just going to model it as a cosine, where t now, that's the current time. So this gives me something that oscillates with a particular frequency. But I know that the data doesn't look perfect like that. So I'm going to do that residual error thing that I did on the previous slide, but I'll add the residual error to the cosine. And that gives me a noisy cosine. And maybe that captures the autocorrelation. Maybe I need to add multiple cosines, lots of frequency components. This is why we characterize noise in terms of its color, because we're actually communicating the frequency components that need to be in these models. So that's what we're doing there. And there are other patterns that you can build into it too. So other ways that, like in here, you can build an auto-regressive model. So rather than basing it on time, you can autonomize it. So you can make it autonomous, meaning make it not depend on time. You can make it depend on previous values. So you say the next value of the price is 90% of the previous value of the price plus noise. That's another way to build autocorrelation. All right, questions on that? Is that clear, that property? All right, these are all things that wouldn't necessarily think of looking for, but you should when you get your data points. The other important thing as you go into this input modeling report, and I will say this over and over again, but there will still be people who submit input modeling reports who make this mistake. Do not try to fit a model to output data. So we only fit models to input data. Wait delays, wait times, things like that, queue lengths, those are things that come out of your model. There's no point in fitting data to them because you won't use that model for anything, because that's the output of your model. So you only fit models to things that go into your model, not things that you then measure on the output of your simulation model. So input data, that's what we do fitting on. Output data, we end up looking at afterwards to validate whether our model matches reality, but we don't fit surrogates to our output data. But I will guarantee that at least one group will gather data for their input modeling report, and they'll gather some input data, they'll gather some output data. They will call it output data, they'll call it wait times, and they'll fit something to it. And they'll say, our wait times had a Weibull distribution fitted to them. And I'll write some remark like, how are you going to use this Weibull distribution? Like, where in ARENA do you say the wait time is Weibull? You don't. You run ARENA, you get wait times out of ARENA, and then you look at them and say, those wait times are shaped this particular way. That tells me something about the performance of the system. But at no point do you need to fit them. So that's the other key point that I want to make there. So do not fit input models to output data. All right, and I think that's basically all the things that I wanted to cover here. We'll talk about more quantitative things as we go into lecture G2 and G3. So let me get your clicker up, and then if you have any questions, feel free to come up. So I will do a short answer for this clicker, and the question I have is finish the phrase, fill in the blank. Do not fit input models to blank. So what is the blank? Do not fit input models to blank. Fill in the blank. And that's all I've got for you. So thanks for your attention.